Okay, here's our homework number 2 video, and we realized that in some situations using a vertical rectangle, do vertical rectangles I guess in red, is not super advantageous. So I recommend that you draw rectangles, starting from the left going to the right. And I notice these rectangles right here, they have a height that is the x squared minus the line y equals 1. This distance, x squared minus this distance, 1. But then I go here, and all of a sudden the height has changed. The height of this rectangle is just the 4 minus the 1. We are not going all the way up to the x squared. And then I get here, and all of a sudden we change again, and the height is now the 7 minus x minus the 1. So I have to find my intersections first. It's not that bad with this x squared. When it's equal to 1, that must be a y, x of 1. And then when x is 2. And then here, 7 minus x, when that equals 4, that's going to be 3. I could just set these equations equal to each other and solve, but it's easy enough to see. And then if I have 6, 7 minus 6 gives me a y of 1. So I need 1, 2, 3 integrals of the sum of these different rectangles that have these different heights. So with the vertical, I need an integral from 1 to 2, x squared minus 1 of my heights. Then from 2 to 3, I have heights of just 3. So this is just a rectangle worth of area that I could find. I don't need an integral. I could use geometry from 2 to 3, but whatever. And then from 3 to 6, I have the 7 minus x minus 1 heights. Gosh, that is very, very involved, which is why in some situations using horizontal rectangles will be advantageous. And let's go back over and see what horizontal rectangles would look like. Well, I would sum up with horizontal rectangles these rectangles that have a skinny height. The height is now a dy, and the width is what it's long. And I see that I'm like summing them up, going from the bottom to the top. That ensures a positive height if I go up. Okay, so I need to be going up. Well, notice these distances, the widths are now consistent. It's this x distance here minus this x distance here. Well, to get x distances, I need to turn these equations into x equals function of y equations. It ends up being inverses. So you add x, subtract y, you get that this equation x equals 7 minus y. That would be the right distance, like going all the way over here to like almost 6. So I have seven minus y. And then this guy, to solve for x, to get a x distance in terms of a y coordinate, if I plug in a y and square root it, I will get an x distance. So I will subtract that root y. And all of a sudden, this is just one integral, one infinite sum, starting from 1 going to 4, making sure my dy's are positive, of a right minus a left. This integral would give you the exact same value as this integral. Isn't this a lot easier to handle than this? Sometimes horizontal rectangles will help us. And, you could spend the time to plug this into your calculator. Maybe I'll just do this really quickly for you guys. And then I'm not going to do this for the future ones, but just for this one. All right, So, math 9, we're going from 1 to 2. We got x squared minus 1, 2 to 3, 4 minus 1. So that's just going to be a rectangle 3 plus 3 to 7. Right, top minus bottom. Sorry, 3 to 6. Okay, so I get 8.83333. Math 9, 1 to 4. You might be freaking out. You're like, how do I plug in y's? Don't worry about it. Just plug in x's. You're going to get the same result. Same thing. Is that cool? All right. Let's look at this situation. Let's start with vertical. So I notice if I start from the left going to the right to ensure my widths are positive, and I forgot to write that up there, I think that the widths are dx. To ensure my widths are positive, I need to be going from left to right. I notice that these heights, until I get to this point right here, the heights are 10 minus 2. And once I get here, my heights change. And these rectangles do not have heights of 10 minus 2. These heights are 10 over x minus 2. Okay? So for vertical, I'm going to need two integrals. One integral from here to this intersection. So that's going to be when x is 1. That's pretty easy to kind of see that when do we get a y of 10 is when x is 1. You could solve this equation so that it's equal to each other to figure this out. And then when x is 5, I get a y of 2. So I go all the way to 5. So vertical, I'm got to go from 0 to 1 of 10 minus 2, get this rectangle worth of area. And then I'm going to have to add, and then go from 1 to 5 of my new heights, 10 over x minus 2. Now, using horizontal rectangles, we notice consistencies. Now, to make sure that with a horizontal rectangle, we have a positive height. So a very small change in y. I need to make sure I go from down to up. And I notice it's the same x distance. It's a right minus left, but there really is no left. It's just going to be this function in terms of an x distance of y's. So if I take a y, plug it in here, I'll get this x distance. That's x distance. Okay, so that's going to be the widths. The widths are 10 over y, and you could say minus 0 because it's x equals 0, or you can just not subtract anything. So this is 2 to 10 of 10 over y. We'll get the same answer for both of those. Okay. Similar situation. I kind of made sure I created these situations so that you see that horizontal will help us. Horizontal will be easier rather than vertical. For my vertical, my top minus my bottom, my width being dx, I'm going from left to right to make sure that dx is positive. But the heights are all root x, or root x minus 0. It's the top minus the bottom. I get to this intersection, and then I switch over, and these heights are 2 minus x minus 0. This intersection, you could solve the equations that are equal to each other, but you can see it's just going to be at 1. Root 1 is 1. 2 minus 1 is 1. And then this intersects when x is 2. I get a y of 0. So I'm going to go 0 to 1, 1, and 2. Now let's switch over to horizontal. Well, to ensure my horizontal rectangles have a positive height, we'll go up. Now the height is a very, very small change in y. I'm going up, so I'm summing them up from the bottom to the top. Fortunately, this intersection is at 1, 1. I just have to figure out what the distances are. Now, this is a right minus a left. It's not minus a 0. It's this x distance from 0 to here minus this x distance here, and that'll give me this width. So I need both of these equations to be solved for x, so I get an x distance in terms of a y coordinate. I'll add x, subtract y, I get x equals 2 minus y. I'll square both sides, I get y squared equals x. So my width is a right minus a left. Sorry, that's 2 minus y. Minus a y squared, okay? These are x distances in terms of a y coordinate. Plug in y, I'll get an x distance. Plug in a y, I'll get an x distance. Subtract them, I get that. I'm summing these up from 0 to that y coordinate of 1. Okay, so 0 all the way to 1. Make sure we're focusing on the y coordinates, not the x coordinates. And we have 2 minus y squared are the widths, and then the height is dy in this infinite sum. Using a calculator, find the line y equals k that splits the previous region into 2 equal areas. So we actually needed to find the area for these, but let's go for it. Well, in this situation, if we think about this y equals k line, we know that this area from 1 to k, this area underneath this line, will be equal to half the total area. So notice we're starting at 1, not at 0. We are used to, like on our quizzes and our past homework, maybe starting from a different value, but we got to make sure we understand we're starting from here. And we had an expression, this is x equals 7 minus y, and this was root y equals x. So right minus left, 7 minus y minus root y. That needs to equal 1/2 the total area. I think I found it. Yep. 8.33. That's 53 sixths. Dividing that by 2, I get 53 twelfths. Duh. Okay, but now we have to find k. Now to do this, we need to get rid of the integral by taking the antiderivative. So I take the antiderivative. Using my antiderivative rules. And now I have to plug in 1 and k, set this equal to 53 twelfths. So plugging in k is easy. It's just like keeps the variable. But then plugging in 1 will produce some numbers. 7 minus 1/2 minus 2/3. This equals 53 twelfths. I'm not going to simplify this at all. I'm just going to type this in to my calculator to solve this, no matter how complex it is. Okay, so I got 7k minus 1/2 k squared minus 2/3 k to the 3/2 minus the quantity 7 minus 1/2 minus 2/3. That will equal 53 twelfths. I'm looking for a y value between 1 and 4. I'm thinking that it's going to be closer to 1. So it might be like not right in the middle, which is 2.5. It's probably closer to like 2. So it's going to be closer to 1 than it is to 4 when we look at it compared to the middle. So I'm looking for something like 2, I think. Second, calc, intersect. I'm looking for this intersection. Enter, enter, enter. 2.038. That looks good to me. .038. All right, it didn't actually find the area here, so let's just like, start off. So here's my y equals k, and then my area from 2 to that k of the right minus the left. The right minus left is just the right minus 0. All right, so 10 over y that's going to equal to the half of the overall area, which I'll just kind of write out like this and calculate right now. Or I could actually plug it into y equals, So yeah, let's do it. I have to get rid of the integral to be able to plug in k. 10 over y, 10 log y. From 2 to k. That's 10 log k minus 10 log 2. That equals this. I'm going to graph and solve. I have 10 log k minus 10 log 2. You can actually simplify this using log properties if you wanted to. And that's equal to 1/2 of the integral from 2 to 10 of 10 over y dy. It's one negative about plugging this integral into your graphing. It might take your graph a while to do. I never recommend graphing integrals, okay? If you're trying to graph an integral, most likely you're doing something wrong. So if you're ever like finding a max or a min or something and you're like, oh, let me just graph the integral so I can find the max and min, I'll just look at it. No, you're never doing that right. 4.472. That's good. That's underneath the midpoint, which is 4.5. No, 5.5. Yeah, 5.5. All right, so there you go. K is that value, 4.472. And I'll do the same thing here because I didn't find the area. This intersection is 1. Here's my line y equals k. I could see it's going to be underneath 0.5, which is the midpoint. So my area from 0, it's nice to see a 0, to k will be equal to half my total area. So integral from 0 to k of my right minus my left are my widths. Will equal half my total area. So that's half of the integral from 0 to 1 of 2 minus y minus 1 squared. Okay, so I get 2y minus y1/2 y squared minus 1/3 y cubed. From 0 to k equals whatever this is. That's 2k minus 1/2 k squared minus 1/3 k cubed minus 0 equals that, and I'll solve that. 2k minus 1/2 k squared minus 1/3 k cubed 1/2. Whatever this number is. Multiple intersections, but we're looking from the one between 0 and 1. We think it's a little bit less than 0.5. Second calc intersect. We can see what the other curve is. So this is the area, 0.58333. No, that would be half of the area. So 1 point something. And there you go. There's my intersection. It's less than 0.5. It's 0.323. All right. Without using your calculator, find the area enclosed using horizontal rectangles. Okay, cool. Well, can't use my calculator, so I'm going to have to find the intersections of these two equations. Set them equal to each other. And I get x squared minus 2x minus 3 equals 0. And I get two x coordinates, x minus 3, x plus 1. So that's going to be 3 and negative 1. I know that this x squared and this 2x plus 3 will intersect like this. This is at negative 1, and this is at 3. Great. I'm not going to be able to do this using horizontal rectangles. I mean, I can. I won't ask you a question like this in the future. This is a little bit too complex to do with horizontal rectangles because this is what we have to do. Let's find these y-coordinate intersections. So when x is 3, this is 9. When x is negative 1, this is 1. Okay, so I got that. Now look at what's going on. Right minus left. The right minus left changes. Usually we like to use horizontal rectangles when things get easier, but this does not get any easier. Now, if you solve for x, you get x equals root y, right? Actually not. You get x equals plus or minus root y. The positive half of this graph, this x squared graph, would be x equals positive root y. The negative half would be x equals negative root y. Okay, and actually what I see is that my first one, and now this intersects at 0, so this is my starting point. My first rectangles from 0 to 1 have a width of a root y minus another root y. So it's a 2 root y. And that's from 0 to 1. And then I'm going to add from 1 to 9, my right, which is root y, and then my left is the y equals 2x plus 3. Well, that's y minus 3 divided by 2 equals x. That is my left. So this is a little bit more complex than it needs to be, but I'll show you how this would be the way you would get it. And you type this in, it is the same as negative 1 to 3 of 2x plus 3 minus x squared. I don't want you to try to find this without a calculator. Let's just like stop here. A little too much here. This one might be a little more advantageous. Not really, but let's go for it. We have y equals negative 2. We have e to the 3x. We have x equals 2. And I'm using horizontal rectangles again. And watch, this is a kind of the same deal. It's not as easy as we might think. Because until here, the width of these rectangles is just going to be this x distance of 2 minus 0. But then the width of these rectangles up here will be 2, this x distance, minus this x distance from this from 0 to this graph, which means I need an x equals y equation coming from here. I have to take the log of both sides and divide by 3. All right, so if I were to at least construct the integrals, I'd go from 0 to, where is this intersection? Where does e to the 3x intersect with x equals 0? Well, if x equals 0, e to the 0 is 1, so this is 1. And then what's this value up here? Where do I stop? Well, when x is 2, this would be e to the 6th. So I need to go from 0 to 1 of 2, and then I need to add from 1 to e to the 6th, the 2 minus log y over 3. And that's what I get. Okay? You don't know the antiderivative of log y, so I'm going to change this to, without using your calculator, set up integrals to find the area. Because like you don't know how to take the antiderivative of log y. But this would be it. It's good to be able to set them up. That's important. Now we're going to go into some of our free response questions. And we are going to find areas that we might have already found just using horizontal rectangles. So sketch them. We see I'm starting from 0. I'm going to this y coordinate. What is this y coordinate? It's 6. So I'm going from down to up to ensure my dy, my height, is positive. My width is this x distance. This x distance will come from this equation where our x distance will equal a function of y's. So I can take a y, plug it in, I'll get an x distance. I will divide by 2 and square both sides, giving me y squared over 4. So that's the x distance. Now, I can do this without a calculator. So 6 cubed over 12. Find this area using horizontal rectangles. All right, well, I see the intersection's at 4. That's nice. If I were to draw my horizontal rectangles, I could see that the height is a very small change in y. The width is the right, which is the x squared function. So that's x equals a positive root y, because I'm over here to the right, not the negative root y. And then here, this x distance will be y over 2. So I got right minus left to get my width. So I got root y minus y over 2. I'm going from 0 to 4, root y minus y over 2. I can find this, actually. So let's do it. Y to the 3/2 times 2/3 minus y squared over 4, from 0 to 4. 4 to the 3/2, the square root of 4 is 2. 2 cubed is 8. So this is 16/3 minus 4 minus 0. That's 12/3. 16/3 minus 12/3 is 4/3. Okay, I think I found that last class as well using vertical rectangles. Okay, horizontal rectangles. I'm allowed to use my calculator. Okay, well, what's easy about this is probably the widths and the heights, obviously. The widths are the right minus the left. It's the line minus the curve. So y plus 2 equals x is the right. The left, I have to take e to the power of both sides to solve for x. X equals e to the y. But the one thing I don't know is these intersections. So since this is a calculator problem, when I do set up my integral, I know it's going to be this right x distance minus this left x distance. But now I need to find my boundaries, my intersections, the y coordinate here and the y coordinate here. So I'm summing up from bottom to top. So I will graph x minus 2 and log x. I will find second calc intersect this guy. Negative 1.84. $1,406. The other guy. $1.1461932. $1.1461932. And then I'm going to find that. Math 9, negative 1.841406 to 1.146192 of right minus left. Enter. Okay. 1.949. I think I've already found that. Log x 5 minus x. Oh! Thought I already did this one, but I didn't. Area. Using both horizontal and vertical rectangles. Okay, great. So it is a calculator problem, I'm hoping. Let's just assume it is. Okay, well, issue is this intersection. I don't know where it is. So if I'm using vertical rectangles, let's just think about that first. I'm going to have two integrals. One from 1, I can see that, to whatever this value is, of my top. That's my log function. And I'm going to have to add from whatever this intersection is to what looks like 5, because like 5 minus 5 is 0, of the 5 minus x. Let's go ahead and find the intersection. Log x and 5 minus x. There it is. 3.6, I can't speak today, 3.69344414. And I'm going to use this y in the future, so I might as well write it down 1.30655866. Okay. All right, so like summing them up from 1 to 3.69344414, and then 3.69344414 of these tops, which is the 5 minus x. So I need those two integrals using those vertical rectangles. Using horizontal rectangles, going from 0 to 1.365586, I have the same right minus the left. Now this would be e to the power of both sides, x equals e to the y, and this would be x equals 5 minus y. So I'm going from 0 to 1.306556 of my right, which is my line, that x distance, minus the left, which is this x distance. And this is what I get. I'm going to find that value because I'm going to need it in the future. Second quit, Math 9. 1.306556 of 5 minus y. I use x's minus e to the y. I'll get the same thing if I typed it in the other way. 2.985. We'll keep the entire thing for the next problem. Okay, so this is an actual question. The horizontal line y equals k divides r into two equal regions, right? But do not solve an equation involving one or more integrals whose solution gives the value of k. So what's great is you don't have to solve, okay? I don't think I ask you to solve either. So this is a good example of like what you are asked to do, make sure you provide. Well, what's the line look like? Y equals k. There's y equals k. The area below it. Well, I'm going to use horizontal rectangles easily to represent the area below it, or else I'm going to have to find these like crazy intersections at these places. It doesn't really make sense to do that and use vertical rectangles. So from 0 to k of my right minus the left, you could say that equals 1/2 my overall area. This works. You can say that's equal to, 2.985. What was the rest of the numbers? 804,105 divided by 2. You could say this equals the integral from k to 1 point, I can't read my handwriting. Is that a 3? 306 of 5 minus y minus e to the y. These are all acceptable right sides of this equation. But the left side should really you should all have that. Would it be easy to find the following area using horizontal rectangles? Heck no. Why do I know that? Look at this. Like my right minus the left is using this same curve. So I'm going to have to split it into like 2 equal parts, which was definitely like tough as we saw with that square root. And then I got like this going on and this, and I got this, and then this, and this. It's like, no, don't do that. Horizontal is not always going to help us. It is definitely going to be easier to use vertical rectangles. The top and the bottom is consistent. All right, I hope we understand this. I hope we're not trying to take easy way outs. It's really, really, really important, especially for the next lesson, to be able to visualize and draw these rectangles and understand dx being a skinny x distance, a skinny width, or dy being a possible skinny height. Dx for vertical rectangles, dy for a horizontal rectangle. That's it. Thank you.